the recording and switch off the video just to make sure that you have a clear voice. Right. Now, if you remember a week ago, we started talking about the stars and their evolutionary process, right? As the first step, we talked about the different properties of the stars, how they are measured. For example, how to measure the brightness of a star, and there is a magnitude scale for that. And then we talk about the color of a star, how do we measure the color, and how to measure the temperature, those kind of things, right? And then we talked about triggering star formation. That means what kind of conditions that we have to satisfy in order to trigger a star formation, right? So we talked about the molecular clouds and what are the conditions that needs to be satisfied in order to have a star at the end from a molecular cloud. And we talked something called Jeans criteria for that, and we discussed about that in the class. And then at the end, we talk about the main sequence, right? So basically, we started talking about this HR diagram, and I explained to you all the axis of the HR diagram and why it is important, right, in stellar evolutionary process. Now, in this lecture, I am completely devoted this section to talk about a star's life when it is on the main sequence of HR diagram, right? So basically, my assumption is that you are well familiar with HR diagrams, and the lecture notes was also available in the Google Classroom. And by the way, the lectures that even I am doing today is now available in the Google Classroom. Right? You may see in the file name, it's a different code name like 322GE, but that is okay. These are basically the same set of lectures I used to do for your previous classes as well, this final set, right? So there is not much that I have to change here based on your syllabus. So I am using the same set of notes. So that's why that name is there, but you don't need to worry about it, right? Now, when we talk about the stars when they are on the main sequence, once again, you can see a picture of a HR diagram here, where you have the spectral class in the x-axis, and the y-axis, you have the luminosity. And one may actually replace this luminosity from the absolute magnitude, I mean, which represent basically the same thing. And also you can see the surface temperature is also given just below the spectral classes. And that should give you an idea the connection between the spectral class and the temperature aspect, right? And this is actually a schematic diagram of HR diagram for large number of stars, right? And statistically, you can see there are prominent features here of the HR diagram. So the one important thing here is that you can see this set of stars right here, which forms a line or closed structure close to a line. And this is what we called as the main sequence. And you can see that statistically, most of the stars lie on this main sequence, right? And there are a minority of the stars that you find in this upper right corner, which we called as red giants and the supergiants. And then in the lower left-hand corner, you have stars that have a higher temperature. However, their luminosity is not that much. So these set of stars are called white dwarfs, right? So you can see that there are different, prominent regions that you can identify here in this HR diagram. And so we are going to talk about each of these sections and why these stars are in these particular regions in an HR diagram, right? So what actually happens is if you take a certain star it will enter into the main sequence at a particular point and will spend some time in the main sequence. The location of the main sequence that this particular star would be. So that means a star may located in this region of the main sequence and maybe in this region of the main sequence, or maybe it can go up to this region in the main sequence. That particular location a star would place in the main sequence depend on its initial properties, and basically it will depend on the mass. You will see it in the next slide. And so what will happen is the star will spend certain time in this main sequence. The position or the location of the main sequence that it will take place will depend on its initial conditions, right? And then after certain period of time, after some certain fusion reactions, they will move into different stage. That different stage should be either to this red giant stage or maybe supergiant stage, once again based on the mass of the star. And then they will start to spend some time on this particular stage, and then and in this particular stage, and then after certain time they will move into this region right here if they are actually low mass stars, right? And there are other things that could happen as well. So this is typically what happened to a star during its lifetime. Now, which path it takes and how long it takes, all these things depends on the initial conditions of a star that we are going to discuss today, right? So in this particular lesson, we will specifically talk about what happened to a star when it is on the main sequence. And after that, we will talk what happens after the main sequence, right? So what we have discussed up to the last lecture is what are the conditions that should satisfy to generate a protos star and then will become a main sequence star, right? So that is what we have discussed in the last lecture, right? So you remember that there should be a molecular cloud and it has to satisfy this genes criteria in order to create a good star. And then that star will be placed on the main sequence at the end, right? And there are certain type of stars that they do not have enough mass to burn hydrogen into helium. And if that is the case, then those stars will not enter into the main sequence. And those kind of stars are called as failed stars, right? Or brown dwarfs. So those are considered as brown dwarfs. And that was what we have discussed at the end of the last lecture. Now, what we are discussing here is what happens inside this main sequence when a star enters into the main sequence, right? So I hope that is clear for you. Now, what is important here is all the stars on the main sequence are at a similar stage in their lives, right? So their stage is similar. That what that means is what they are doing is similar, but they will have different ages, right? So their ages is different. So there may be young stars. Young stars means the age is less, and there may be some stars that are a little bit older. And however, what they are doing at present is similar. So that is the most important. Basically, all these stars that you saw on the main sequence line, what they are doing is they are burning hydrogen in their core region of the star. And once they burn hydrogen, they will be converted into helium, right? So this will be doing so they will do it at a constant rate. So this is what actually happens, or the process that actually goes on for the stars in this main sequence, right? The thing that you need to understand here is each and every star on that main sequence will do this, right? The only difference is that these stars have different ages. So their age is different depending on the location of the stars on the main sequence. However, what they are doing is similar. right? So that's what you have to understand. Now, you know that hydrogen is the most abundant and the slowest burning of the fuels that a star burn in its lifetime. So what they have mainly is hydrogen, because hydrogen is the main component that you see in the interstellar medium. So the stars are made from these molecular clouds in the interstellar medium, but mostly what they have is hydrogen. And hydrogen is also the slowest burning fuel. So it's a fuel that burns very slowly. So therefore, normally all these stars spend most of their lives in the main sequence, right? So most of the stars will spend the lives in the main sequence. Now this is why when you plot an HR diagram for a particular star cluster, in fact, statistically 90% of the stars will be found on this main sequence, because at any given time, this is the stage where most of the stars, spend their life. So it is, it makes sense to find most of the stars on the main sequence stage, right? And the other thing is these main sequence stars are very stable. So that's because, once they convert hydrogen into helium, there is a fusion reaction going at the central region of the star, which creates a lot of temperature, a lot of heat, and that create a pressure towards the outward direction of the star. And at the same time, because of the gravity, there will be an inward force. And it is the balance of these two forces keep the star stable on the main sequence, right? Right. So as an example, so I have given here a small table just to give you an idea some of the properties of these main sequence stars. And you can see that if the mass of a star is 1 solar unit, so that means typically a star like our sun, right? So it takes 1 times 10 to the power 8 years for the formation of these kind of stars. Now you can see that this process takes so long time, right? And then once the star is formed and enter into the main sequence, this star will spend around 9 times 10 to the power 9 years in the main sequence. And after that, it will move on to the giant phase. So that is the top right-hand corner of that HR diagram. So that will be again 1 times 10 to the power 9 years spending on that giant phase. What you can see here is when you go to the second row, you have a star of 5 solar mass. So it will take around 5 times 10 to the power 6 years to form, and it will spend around 6 times 10 to the power 7 years on the main sequence, and then on the giant phase 1 times 10 to the power 7, right? And if the initial mass of the star is 10 solar masses, that means the mass will be 10 times compared to the mass of the sun. It will spend only 6 times 10 to the power 5 years on the formation stage, and on the main sequence, just 10 to the power 7 years. And on the giant phase, 10 to the power 6 years, right? Now, what you can see from this data is that when you go from top to bottom, the mass of the star has increased starting from 1 up to 10 solar masses. And then the time it takes for the formation of these stars has increased. So it has decreased as well, right? So it basically increased to this direction. So you can see that when mass increased, larger the mass, it takes us a relatively smaller time to form. These numbers are very large. I mean, if you take the relative time, it's still smaller for larger stars. And when you look at the amount of time that they spend in the main sequence, you can again see that the time they spend in the main sequence will become lesser and lesser when the star gets or the initial mass of the star gets larger and larger, right? Same thing for the giant phase as well, right? So everything get, everything happens. What is the idea here is everything happens faster for these massive stars. So the larger the initial mass of the star, the quicker it will go through the process of the formation and the evolution. All right. So that's what you can see here. The reason for this one is actually because once you have a higher mass, your gravitational, contraction is more effective, so that the stars will, contract faster, so that will increase the central temperature faster as well, which will give fuel to start this fusion reactions more faster compared to the low mass stars, and because of that they will go through the evolutionary process quicker, right? So these kind of this is one of the very important features that you have to keep in mind. And in terms of the now this graph again shows kind of the same thing based on the surface temperature and the spectral type. All of you know that when you go for the class O and B type stars, they will actually have a higher temperature, right? According to the spectral class classification, like 54,000 and 30,000 Kelvin respectively. And when you look at the mass of these stars when they are on the main sequence, these high temperature stars will have higher mass as well. For example, when you take an O-type star, it will has a temperature around 54,000 Kelvin, and at the same time, the mass will be around 40 times the mass of the sun, or 40 solar mass, right? Like that, when you go down in these spectral types up to the end, as you know, the temperature will go down as well. And at the same time, the mass of the stars will go down as well. And this is, by the way, all these informations are based on this HR diagram, right? If you remember this line right here, the main sequence. You know that the high temperature like O type is somewhere here, M type is somewhere here. So the high temperature stars are the stars in this region. So they will have higher temperature, and O and B is spectral class, and their mass is larger as well. When you go down with the line of the main sequence, their spectral classes will move on to the M region, and at the same time, that means the stars will become cooler and the masses will be smaller. So the stars in this region of the main sequence basically will have a smaller mass, right? Basically, you can tell this as a mass sequence as well. Now, you know that there is a separate section that in astronomy we use for intelligent life on the other planets, right? So when you are searching life for the other planets, it will be a big waste of time to search around O and B type stars, right? Because when you are searching for other planets for some intelligent life, then you first need to find the solar system, right? To find the solar system, you should have a central star, right? So around that star, there should be planets. However, if you are trying to look at the solar system or planets, we call this as exoplanets around O and B type stars, that will be a pretty big waste of time. The reason is, as you can see, these high mass and high temperature stars, they don't live that much long in this main sequence phase where you burn hydrogen into helium. As you, if you remember in the chapter that we talked about the sun, this burning hydrogen into helium and producing energy is the main source that we have as the energy source for all these stars, sorry, all these planets, right? Even in our solar system. So if that procedure goes through very quickly and finish off especially that means the life in the main sequence is shorter. For example, now O type stars, you just have 1 million years, right? So if that the life that they spend on the main sequence becomes shorter and shorter, that means there is less probable that that particular star will support to planets with some intelligent life, right? Because the star itself will not survive for a long time. That should, you should give some time for that surrounding planets to create life and then sustain it as well. Right? So it's very less probable that these O and B type stars can do that, because they will only spend a very little time on the main sequence. That means burning hydrogen into helium. So they will quickly finish up their fuel and will move on to the next stage, right? So that is something extra. And this HR diagram again right here again explains the same thing. So I just have more information there. And you can see the spectral type is here in this x-axis, and in the upper region I have the surface temperature as well, which basically tells the same thing, same trend. And on the y-axis, I have the luminosity increasing into this direction. So that means the brightness also should increase in the magnitude scale. So I have put the absolute magnitude here, which is related to the luminosity. And you can see the number goes down when you go up. And all of you know, I guess now, that when the number is smaller, that means the star is brighter, right? Right. Now let's look at, once again, there is the main sequence on the HR diagram. Now let's look at the masses of these stars on the main sequence, how they looks like. You already know that mass is one of the most fundamental properties that you can have. Basically, the mass actually determines the luminosity and the surface temperature of a star. And of course, once you have the mass, actually also defines where on the main sequence a particular star will reside, right? Basically, the higher the mass, they will go into top left-hand corner of the main sequence, while the lower or low mass stars will go into lower right-hand corner of the main sequence. So there you can see clearly that it is the mass, initial mass of a star that decide where a particular star will be on the main sequence, right? And as I told you, I have it mentioned here as well, the most massive main sequence stars have the highest luminosity and the hottest surface temperature. And the least massive main sequence stars have the lowest luminosity and the coolest surface temperature. Now, to understand this is again an HR diagram that I have mentioned the relative masses of the masses that you could have for each region of the HR diagram. Now you can see that the stars in this top left-hand corner. So these stars have masses like 60 solar masses, 37 solar masses, then 23 solar mass, and then 17.5 solar mass, like that. Stars that are on the top left-hand corner of the main sequence usually have the higher masses, right? So when you go down towards the lower right-hand corner of the main sequence, you can clearly see that the mass of stars will go down, right? So because of this kind of mass trend that you have on the main sequence, you can also call this the main sequence stars as a mass sequence as well, right? Because when I tell you like there is a star on the top left-hand corner of the main sequence, you should get the idea that, okay, this particular star should have a higher mass, higher temperature, and a higher luminosity, right? So the relationship in between each of these, in between these parameters like the luminosity and the temperature and the mass, when it comes to the main sequence is very important, because based on those properties, we can, derive a lot of things. Right? and make decisions about the stars, what will happen to that star in the future, those kind of things, right? And you can see that our sun is somewhere around the close to the middle of this main sequence. So it's a kind of an ordinary star. There is no specific thing about the sun, right? It's not a high mass star either or low mass star. So it's an ordinary star, right? And the other thing is you can see that these stars in the top left hand corner, they are high mass and they have the higher temperature because they fall into this region, right? And at the same time, when you go for these low mass stars, they fall into this 2500 Kelvin region. So they are in the lower right hand corner of the main sequence, which means their temperature is lower as well. So we used to tell that these stars are relatively cool stars compared to the stars in this region. We used to tell that these stars are relatively hot stars, right? And you can see that the importance of this diagram, right? You can basically, we can explain everything about stars on the main sequence using this HR diagram. Right. Now let's look at what these stars are doing when they are in this main sequence. Now we know that different properties of the stars and how they are placed based on their initial mass. Now, when you take these high mass stars, as I told you before, they will use up their fuel very quickly, right? That's because their mass is larger, so their gravitational interaction is more stronger. So they will quickly increase their central temperature, which will lead to rapid burning of hydrogen into helium. And because of that, high mass stars use up their fuel very quickly. And these most massive stars, such as spectral type O stars, will spend only few million years on the main sequence. Compared to the low mass stars, they will use up their fuel very slowly. And the least massive stars, like spectral types close to M type, will spend up around trillion years on the main sequence. Because when you have a smaller mass, their gravitational contractions happen slower, so they will it is true that their mass is smaller, so they have less material, but at the same time, the gravitational contraction is slower, so which means their nuclear fusion reactions will be slower. So because of that, they will keep on burning hydrogen into helium for a long time because of that reason. And as long as they burn hydrogen into the helium at their cores, the stars will remain on the main sequence for that time period. So which is basically around trillion years for these low mass stars, right? Now, you may be wondering how about what will happen to our sun, right? Because that is important. As you saw in the previous diagram, sun is right here, around, close to middle, but not exactly at the middle. So if you think about the sun is somewhere in between of these spectral types. So basically it's a G-type star. So maybe it's important to know the spectral type of the sun, right? And that sun will spend around 4.5 billion years on the main sequence. So that is the estimate, right? Sorry, I think I worded it in the wrong way. So sun has already spent around 4.5 billion years on the main sequence, and it will continue for approximately another 5 billion years on the main sequence, right? So this information tells us that we are safe for another 5 billion years as long as there is no any other external effects on the sun. Because sun will stay like this for another 5 billion years, burning hydrogen into helium and providing us enough, energy, right? So that's why, moving into the solar energy will not be a problem as long as we can, solve all these technical issues that we have, right? So that is something important for us about the sun, right? So that is what happens on the main sequence. So in the main sequence, once again, if I summarize, they are burning hydrogen into helium. The the higher the mass that you have on the main sequence, the faster they will burn hydrogen into helium, and then they will end up having all the fuel at the end, right? And the smaller the mass, the slower the reactions. Because of that, they will continue to burn hydrogen into helium for a long time and spend their time on the main sequence for trillions of years, right? Right. So then now let's look at what happens when the main sequence starts run out of its hydrogen. In this central region, you burn hydrogen into helium, but there will be a day that we have consumed all the hydrogen in the central region of the star, right? So basically, we have done with all the hydrogen, and all the hydrogen has converted into helium, right? Now, when we are trying to find the answer for this one, this will take us to the next stage of stellar evolution. Now, in the main sequence, hydrogen burns into helium. So that's mainly what happens. Now, the next question that we have is what happens after that? Because at some point, all the hydrogen will be burned up and converted into helium in this central region, right? There is hydrogen, by the way, on the outer core of the stars as well. Now, answer to this question will bring us to the next stage of the evolution of a star, and that is stars will remain on the main sequence until it runs out of hydrogen in its core, right? In the core, once the star is done with all the hydrogen in its core region, then the stars will begin to change at this point. Now, for our sun, we will have enough hydrogen in the core region that converting into helium for another 4.5 billion years. So our star will be stable for that much of time. So that's why we are not worried too much about that at this particular point, right? Now, what happens is when this hydrogen is converted into helium in the core region, what you will have at the end is a non-burning helium ash at the end. So that means you will have this helium, and we have a specific name for that. That is non-burning helium ash at the central region or the core region of the star, right? However, if you have done some fusion reaction physics about some nuclear physics, you know that there should be a certain temperature for hydrogen converted into helium, and then to start burning helium, you have to have more higher temperature, right? Now, in the central region of a star, there is enough temperature to burn hydrogen into helium. But once you have the helium, the star is not yet hot enough to burn the helium, because then you have to increase the temperature again to start burning helium, right? So at this point, what happens is, in the central region, you have helium ash, and the temperature is not hot enough to start the helium fusion. However, what happens is hydrogen burning continues in the shell surrounding the core. So what we have been talking up now is about the core region of the star. However, there are different shells outside the core, and in this shell region, you will still have hydrogen, and you have enough temperature to burn hydrogen in those shells surrounding the core, right? And actually, this point, what happens is, now, since you are done with fusion reactions on the core region of the star, you are not producing, fusion reaction. So that what happens is, you are not basically increasing the pressure in the central region when you are not producing any fusion reactions, right? So when the pressure is not increasing, however, the gravity is you cannot control the gravity. Gravity continues to collapse the star into the central region. So what happens is, at this particular stage, you will lose the balance between the gravity and the pressure. Now, all these steps that we are talking, so basically a balance between gravity and the pressure at some time, right? So once you lost the balance from one side, now in this particular situation, once the helium fusion is hydrogen burns into helium is over, then you don't have enough pressure creating to give this outward first. Because of that, the balance will be lost. and as a result of that, the star will continue to collapse again, right? So the core region will begin to collapse, and then what will happen is something like this. So this is kind of a structure of a star at this particular point. As you see here, at the central region, you are done with all the hydrogen converted into helium. Now you have an unburning helium ash. However, there is a shell outside that. Yeah, you can burn hydrogen in that shell, and then you have an envelope outside that, which we called as an unburning envelope, right? Right. Now what happens is the star is now readjusting its balance between the pressure and gravity, because there is nothing to stop the gravity at the central region when you do not have these fusion reactions and the pressure created. Then the star will continue to collapse, and when when it is collapsing and collapsing, that means kind of uh, what do you call this? You kind of continue, because of the gravity. The star continues to collapse. Now, as a result of that, when this collapse happens, the central region gets heats up again, right? Which means it increases the temperature at the central region, right? I mean, this is in day-to-day life, you can think about the same situation, right? So there is nothing different once you try to, because of the gravity, if you contract something more and more, then in the central region, there will be a temperature created and the things will get heated up. The same thing happens inside the star as well, right? And as a result of this, the core heats up, the hydrogen shell that's surrounding the core region will move outward region, right? Since the temperature is higher, when once again, what happens is, because there is no pressure force creating to the outward direction from the core region, the star will continue to collapse as a result of gravity. And when this collapse happening, the core gets heated up again because of the collapse, right? Once the core heats up, the hydrogen shell that is around the core will move towards the outward direction. So that's because of the higher temperature that is, creating, right? And as a result of that, the outer parts of the star will expand, right? And once the outer parts expand, what happens is the surface area of the star will increase. And if you remember, about the properties of the stars, the luminosity of a star depends on two things. So that is from the Stefan Boltzmann law, temperature is one factor, and the other factor is the surface area. Now, in this particular situation, what happens is, because of the expansion of these shells, the surface area of the star will increase, and as a result of that, the size of the star will increase, and because of the increase of the surface area, the luminosity will also increase, and at the same time, once the star get expanded, once it get expanded, it will be, the distance between the central region and the outer region of the star will decrease, and that will decrease the surface temperature as well. So basically, it's a reduce of the surface temperature. However, the luminosity will increase as a result of higher surface area, right? Now, when a star enters into this particular region, these large cool stars are called as red giants, right? And this is a diagram to show you what actually happens there. A hydrogen burning shell. Hydrogen shell burning on the red giant branch, and you can see that you have the helium core right here, which are done with hydrogen burning, and then you have a hydrogen burning shell. So when this hydrogen burning happens, it will increase the temperature in the core region. That increase will lead to the expand of the star because of the increase of the radiation pressure. And once it get expanded, because of the expansion, it will get cooled down, right? However, temperature will decrease. However, the surface area will increase. And because of the increase of the surface area, their luminosity will remain still the same, even though they are cool stars, right? And here is just an example of what I have mentioned about the relative. If you think about relative sizes of the stars, you can see right here is the sun, which is our star, and here is a delta boost, which is a giant star, and then here is a Psi Cygni, so which is a red supergiant star. And if you the three images are actually drawn into a scale, just to show you that how large is these giants and supergiant stars when it go into that particular phase, right? When they are get expanded in the process that I have just discussed with you, their sizes will be increased to a very large amount, right? Now our sun will also go through this phase at a certain point. However, it will take another 4.5 billion years to start this particular phase, because if it is in this kind of phase, like a giant phase, we will be in trouble, right? The reason is, you will see the sizes of these giant stars and you will see why it is. Now I have a comparison about of a supergiant star with our own sun, and you can see the mass of the sun is 1 solar mass. And the Betelgeuse is a star that belongs to the constellation Orion, which is the brightest star in the constellation. And usually the mass of the Betelgeuse is 16 solar masses. And if you look at the radius, 700,000 kilometers for the sun, but the number is very large for the Betelgeuse, right? And the surface temperature, the sun has a little bit higher surface temperature, but compared to the temperature of the sun, actually Betelgeuse is a little bit cooler. It's not that much high in temperature. That is because the Betelgeuse in this giant phase, right? So it goes through the exact similar steps that we just talked. And the core temperature, by the way, it's a large value. We are basically focusing on the surface temperature here. And the luminosity for the sun, it's just 1 solar luminosity. However, for the Betelgeuse, it's around 46,000 solar luminosities, right? And then the average density of the star is, the sun has a larger density while the Betelgeuse has a very small average density. And the age for the sun is 4,500 million years. Because of the Betelgeuse is a very high mass, its age is very less, it's just 10 million years, right? And in the picture, I can show you what will happen to the sun when it becomes a red giant, right? So this is how the sun looks like when it is in the main sequence. So that is the diameter right now is 1.4 times 10 to the power 6 kilometers, right? However, if you look at the sun as a red giant, because one day it will become a red giant, this is how the sun looks like when it becomes a red giant, right? Now the diameter of this red giant, when it becomes a red giant, is actually 1 astronomical unit. Now, if you remember what is 1 astronomical unit, 1 astronomical unit is the distance, average distance from Earth to the sun, right? Now, this is why that we are more concerned about these evolutionary phases of the star, because if one day when our sun becomes a red giant, its diameter will become around 1 astronomical unit. So that means the sun will touch the surface of the Earth, right? So there will be no distance gap between that when this happens, right? So this is the prediction that we have from right now, but it will take at least around 4.5 billion years for this to happen. So that is why we are, safe and not worried about this right now. But you need to understand sun is also a star. So it will go through the same kind of evolutionary processes that we are talking right now. Right? Right. So here is again just to give you some insight about the Betelgeuse star, because we have been talking about it. Here is that Betelgeuse star. If you look at the constellation Orion, and this is not visible actually at present on the sky, and just check the constellation around, December, January, February, that kind of months. This is a very clear constellation up in the sky. And in one of these corners, you will see a kind of, reddish or yellowish color bright star. It is very easy to identify this star on, because that is the brightest one. And that is the Betelgeuse star. And Betelgeuse is now considered as a giant star. And you can see that the size of the, size of the Betelgeuse star will expand from here to here. And if you think about the size of the Earth's orbit, it's actually this much smaller, right? And you can see how large is this star, right? And size of the Jupiter's orbit is this much smaller. So the diameter of this star Betelgeuse is even go beyond that, right? And this is also the first direct image ever made of a surface of another star, right? So this is one of the direct images made of the surface of a star. Right, so this is just to explain you how a giant star will looks like in terms of the sizes, because we can talk the numbers, but you don't feel it, right? But when I tell you it in this way, you can see that how large is these stars. Right, now let's look at what is going on in this red giant phase. As the red giant star ages, what will happen is, now we know that helium fusion is over, and then you have this hydrogen burning shell. Due to the gravitational contraction, again the temperature will go up, and because of that higher temperature, the star will get expanded, right? Once it is get expanded, it will become cooler and move on to this giant phase. When a star reach to a giant phase, what will happen is, while all these things happening, because of this gravitational contraction, the central temperature continues to increase, right? And once this central temperature reaches to a value of 100 million Kelvin, as I have mentioned here, that is the temperature needed for the helium burning as a nuclear fusion reaction, right? So then the helium core will begin to ignite, right? So once the helium burning begins, this is a very explosive event, especially for low mass stars. That is the masses with less than about the twice that of the sun. So that means this basically happens for these stars in the lower right-hand corner of the HR diagram. And we have a specific name for this helium burning for these kind of low mass stars. We call that as a helium flash, right? Now what happens is, when helium burns, you will get the next material in the periodic table, right? So that is carbon. So once the helium fused, it will create carbon and or some oxygen in the core, right? Once this happens, then the star will be stable, right? And when you have all the low mass stars, since they have similar luminosities in this stage, we call this particular region as the horizontal branch of the HR diagram. That is, if you look at this diagram, you can see that this is the red giant branch that will go into the red giant phase. You can see that I have drawn it into the low mass region, because this is what specifically happened for low mass stars. By the way, high mass stars will go through the same process, but they will become supergiant stars. And then once this helium flash happens, the star will become stable, and most of these stars will have kind of similar luminosities, right, in this region. So that is what we called as the horizontal branch stars, right? And this is what actually happens inside these stars when helium burns. Basically, two helium atoms or alpha particles become a beryllium, and beryllium is not stable, so it will go to combine with another helium to make carbon. So that's how helium is converted into carbon, right? And then there may be events or instances that carbon will catch another alpha particle and become oxygen. So that's why I have told that there will be some oxygen as well in this process. Right, so this particular diagram basically shows you different evolutionary tracks of stars of different masses. The solid, the black line shows the predicted evolution time. You can see that these tracks, we are called this as evolutionary tracks. Now for the time it will take for different stars with different masses to reach to these giant phases. And you can see that for the high mass stars which are in this region, it will take only 1.2 times 10 to the power 7. And however, when you take a low mass star, let's say one solar mass like our sun, it's take 11.4 times 10 to the power 9 years to go into this stage towards the giant region. Like that, the lower the mass, like this, it will take a longer time for going to the next step of this evolution, right? So that is the final message that I can tell you about this evolutionary process. Right, so that is the end of that section. Basically what happens to the stars that are in the main sequence. Anybody have any questions up to here about this section? No questions? Right. So let me then right. So let me then stop the lecture from here. So I'm not going to go for a longer period as we have enough time now to complete the lectures. So this is your 20th lecture. So there will be 10 lectures to go in the next month. So the whole month we'll have 10 hours to complete. So the next day, I would like to talk a little bit about star clusters, because I think this is a good point to start talking about star clusters and how they are related with these HR diagrams, right? So that is one important thing. So what we have discussed today is about the life on the main sequence, the stars, and what happens after the main sequence with these different fusion reactions. And on the next day, I will start talking about the star clusters, just to give you an idea how these star clusters are related to different, helping to understand different evolutionary stages and properties of stars. And then the next probably 2 or 3 lectures, I will go on to talk about what happens for these different what will happen to stars in different phases after the giant phase, right? Specifically, we will divide the sections into like what happens to low mass stars and what happens to high mass stars separately. Basically, low mass stars will become white dwarfs, and then high mass stars will become neutron stars and black holes. So we will talk and study about those two separately in the coming lectures, and I expect within next 3 or 4 lectures, probably 3 lectures, we will be able to finish those 3 sections about stellar evolution by talking up to neutron stars and black holes. And once it is done, I will move on to the sections about the galaxies and cosmology, which is the last part, right? Right. So if you do not have any questions, let me stop from here. Shall we have a lecture on tomorrow morning as well, like this? I don't know whether